So let's now prove the result for upper Riemann sums. So again, we'll let D2 be a refinement of D1, and we want to show that if that's the case, that the upper Riemann sum of the function f over the dissection D2 is less than or equal to the upper Riemann sum over the dissection D1 of f. And again, the way we're going to do this is pretty much exactly the same as what we did for the lower Riemann sums. We're going to consider each of those intervals from the original dissection D1. So here is our overall interval AB. Let's say these are the points of the original dissection D1, which we'll call the x cuts, so x1, x2, x3. And just for simplicity, let's say we only refine D2 very simply, and we just make one additional cut, and we'll put that in there, and we'll call that the y1 cut. So now when you make the upper Riemann sum over D2 of f, the components from all of these three intervals, this one, and this one, are going to be exactly the same as in the sum for the upper Riemann sum over D1. It's only here that's going to change. So in the D1 dissection, the component that you'd have had, and I don't want to do it in red, that won't show up well, the component that you would have had contributing to the upper Riemann sum would have been x2 minus x1, the length of the interval, times the supremum of the values of f over that entire interval from x1 to x2. Whereas now in the dissection D2, it's going to be x2 minus y1 times the supremum of x as an element of y1. Oh, what am I doing here? No, that's not right. So supremum, the value of f over, this should be, oh, wait, what am I doing here? Oh no, I was right. Apologies. So x is an element of y1 to x2. So I've done the second part of the interval first, and then plus x1, no, apologies, my brain will come back on in a moment, plus y1 minus x1, which is this length here, times then the supremum of values of f, where x is allowed to vary over that interval x1 to y1. So let's just check that that's correct. So we've got y1 minus x1, which is this length here, times the supremum of the values of f over that correct interval from x1 to y1. And here we've got x2 minus y1, which is this length, times the supremum of all values of f over that correct interval y1 to x2. And it is going to be the case that this bit here is less than or equal to this bit. And the reason, of course, is that these suprema are guaranteed to be less than or equal to this one. So, as we did previously, we could rewrite this by splitting x2 minus x1 into this length plus this length. So we could rewrite this as x2 minus y1 times the supremum of values of f over that entire interval from x1 to x2 plus, and then the other part of that interval, which is y1 minus x1 times the supremum of values of f over that entire interval x1 to x2. And the reason we've done that is because it allows for easier comparison. We can now compare this one directly with this one and this one directly with this one. And we know that this one is guaranteed to be less than or equal to this one because suprema work in the absolute opposite way to infima. So again, just a bit of basic set theory. If we have two sets, x and y, and again one is contained within the other, then the supremum of the one that is contained is guaranteed to be less than or equal to the supremum of the larger one. So again, just a basic picture. If these are some of the points that are in that set X, then here is the supremum of that set. If you then go to a bigger set that still contains all these red points, then the supremum will remain the same if all of the points that you add in are down here, like I've shown in blue here, but what if you add one like that? That will then suddenly move the supremum up. So the supremum of the larger set is guaranteed to be greater than or equal to the supremum of the included set. So these sets are contained inside this set. So this one's contained inside this one is contained inside this one. So all the values of f in a set here is contained inside all the values of f over this interval. So this supremum is guaranteed to be greater than or equal to this supremum, and it's also guaranteed to be greater than or equal to this one. So multiplying them then by constants maintains that inequality. So we can put some inequality signs here. This one, these two here, have that inequality relationship. This one is guaranteed to be greater than or equal to this one. And these two here, again, have that inequality relationship. This one is guaranteed to be greater than or equal to this one. So just combining those two inequalities together, when you add these two things that are both greater than or equal to these two, then their sum is going to be greater than or equal to their sum. And therefore this is greater than or equal to this. So whilst all the other parts of the Riemann sum for D1 and D2 remain the same, here it doesn't, and you have this inequality relationship. Therefore, overall, you can say that the upper Riemann sum over the smaller dissection is guaranteed to be greater than or equal to the upper Riemann sum over the refined dissection. Now, of course, it could be the case that this supremum actually equals this supremum and this one equals this one, just by chance. If you pick a correct function, you can imagine how that could work, in which case they will be equal to one another. So that's why the equality is still here. So it could be the case that they are equal to one another, but more generally, this one could be smaller than this one. So I have just two more things I want to show you about Riemann sums, and then we can actually move on to Riemann integration. So the first one is pretty obvious. So if you have a dissection, just one dissection now, D, then it is always the case that the lower Riemann sum over that dissection is going to be less than or equal to the upper Riemann sum over that dissection. This follows immediately from the definition. So let's say this dissection has n pieces. You can just compare the two sums here. So the lower Riemann sum is the sum from I is equal to 1 to n of xi minus 1 times then that infimum of the values of f over the corresponding interval, xi minus 1 to xi. And then the upper Riemann sum is the sum from I is equal to 1 to n, and then you've got all these same interval lengths here, xi minus 1, but this time they're all being multiplied by the supremum of the value of f over the same corresponding intervals. So xi minus 1 to xi. So, picture, here is our interval AB. For simplicity, we'll just have our dissection as 3 pieces again. And for each one of these intervals, in the lower Riemann sum, you are multiplying the length by the infimum of all values of f over that interval. And in the upper Riemann sum, you're multiplying by the supremum. So it is the case that that infimum values of f over all values of x in that interval is always going to be less than or equal to the supremum of the values of f over that interval, xi minus 1 to xi. And you'll have equality if and only if it's a constant function over your the part of the interval that you've got, the interval that you're considering in the dissection. So if it's constant over this interval, then the infimum and the supremum will be equal. They'll both be equal to that constant. But if it's not constant, if just one value differs from all the rest, then the infimum and the supremum will be different, and the infimum will be smaller than the supremum. So in general, the infimum is always going to be less than or equal to the supremum, just by the definition of infimum and supremum. So you can then compare each of the corresponding terms here. So for I is equal to 1, this term will be less than or equal to this term. For I is equal to 2, the term here will be less than or equal to the term here. And then combining all of that together, you get that this sum has to be less than or equal to this sum, and therefore the lower Riemann sum over the dissection must be less than or equal to the upper Riemann sum over that dissection. So that's the first pretty obvious point. The second point, which is less obvious and is much more useful, is the fact that this holds true even if you're talking about two different dissections. So if we take the dissection D1 and the dissection D2, which are different dissections, then it is still the case that the lower Riemann sum over the dissection D1 is less than or equal to the upper Riemann sum over D2. So how can we prove that? Well, the way we do it is by finding a third dissection, which I'll call D bar, which contains both of these two dissections. So all the cuts from both of them have to be inside this refined dissection. So I can show you this on the picture. So if we have our interval AB, let's mark our cuts for dissection D1 in red. So let's say it's got these cuts here. And then if we draw another interval here, which can show the dissection D2, and we'll show this in blue, then it could be a totally different dissection. It could be something like this, so a very different dissection. Those are the points that we're cutting in D2. So this is D2, this is D1. What I can now construct is this D bar that is going to be a refinement of both of them, and it's going to contain all of the cuts from both of them. So here is A, here is B. So we're going to have all of those cuts from D1, which I'll try and put on here in hopefully equivalent positions. And now we're going to have all of the cuts from D2, and I think that first cut in D2 is just to the left of that second cut in D1. And then I'll put one there, and then we've got two in there, and then those final two seem to be to the left of that. I think that that is a fair representation of it. So we've got 6 cuts there, we've got 6 blue cuts here, we've got 4 there, 4 here. So this new dissection with all of these cuts is then a refinement of both of them. And we can use this to prove this inequality because we know something about the relationship between the lower Riemann sum of a dissection and a refinement of a dissection. So what we showed is that if D bar is a refinement of D1, we know that the lower Riemann sum of F over D1 is less than or equal to the lower Riemann sum over its refined dissection. So that is what we proved earlier. So I haven't got it on here anymore, but of course we proved the equivalent thing for the upper Riemann sums. So we've shown that if you have a refined dissection, which D bar is a refinement of D1, then the lower Riemann sum over the refined dissection is greater than or equal to the lower Riemann sum over the original dissection. We also know that the lower Riemann sum over the refined dissection D bar is less than or equal to, and again I'm switching notation back to the capital S, is less than or equal to the upper Riemann sum over that refined dissection D bar. That's what we've just talked about here. So if you take any dissection, the lower Riemann sum over that dissection is less than or equal to the upper Riemann sum over that dissection. So we know this, and now what we know is because D bar is a refinement of D2 also, then the upper Riemann sum over D bar is guaranteed to be less than or equal to the upper Riemann sum over D2, the less refined dissection of F. And this therefore gives us what we want, that this lower Riemann sum over D1 is less than or equal to the upper Riemann sum over D2 by transitivity. So I'll repeat that argument. So we've got these two dissections, D1 and D2, totally separate, distinct dissections. None of their cuts are the same. And we want to show that the lower Riemann sum over the dissection D1 is always less than or equal to the upper Riemann sum over this other dissection D2, the way we have proven that is by creating a third dissection which has all the cuts from both of them in it, and this therefore is a refinement of both of them. And what we know is that the refined dissection will give better lower and upper Riemann sums than the original two dissections. So in particular, the lower Riemann sum over the dissection must be greater than or equal to the lower Riemann sum over D1, and the upper Riemann sum over this refined dissection must be less than or equal to the upper Riemann sum over D2. We then know, because for any dissection the lower Riemann sum is less than or equal to the upper Riemann sum, this part, and then by transitivity we have that the lower Riemann sum over D1 must be less than or equal to the upper Riemann sum over D2. And that actually is really powerful because we didn't make any constraints about D1 and D2. They were two just general dissections, and now what we know is that any lower Riemann sum over any dissection is always guaranteed to be less than or equal to the value of the upper Riemann sum, and that is really, really powerful. This is essential understanding in the definition of the Riemann integral. So if you think of all the possible dissections there are, and there are infinitely many, so many different dissections, what you could then think about trying to do is collecting together in two enormous great sets all the values of the upper Riemann sums over every dissection. You could imagine that as a concept. You could also imagine the equivalent thing for the lower Riemann sums. So what I mean by these things that I've written here is this is supposed to be the set of every possible value you could get for the upper Riemann sum, and this is supposed to be the value for every possible value you could get, the set of values of all values that you could get for lower Riemann sums over every possible dissection. What we now know from this inequality is that everything in here is less than or equal to everything in here. So as sets, if we plot this one in red, all of these points might be down here, and there are so many of them, you know, I'm not going to be able to draw all of them. Huge number of possible values, unless of course we're dealing with a very simple function. If we're dealing with a constant function, then of course there's only one value for the upper Riemann sum and only one value for the lower Riemann sum, no matter what dissection you take, and that is the area under the curve. But any more complicated function other than a constant function is going to have more values than that. In general, there'll be a huge number. Even if you just take something like x squared, y is equal to x squared as your function, or f of x is equal to x squared as your function, which we will do as an example in just a while, you know, there's going to be a huge, great number of possible values depending on the different dissection you take. But what I'm saying now is because of that inequality that we've just shown, what we know is that every value in this set, you take any value, and these blue points are supposed to represent the possible upper Riemann sum values, any value in the blue set, it's going to be greater than or equal to every single one of these values in the red set, and that holds true for any of those things that you pick in the blue set. So this set, as a set, is greater than or equal to this set, meaning that every value in it is greater than or equal to the corresponding value in that. So that's a very powerful inequality that we've just shown there.